We're going to be moving on to our next talk from Cameron Hummels. He's going to be talking about synthetic observations of galaxies with Trident and YT.
All right, so I'm Cameron Hummels. I'm a postdoc at Caltech, and this is going to be a slightly different talk than the kind of talk that Matt gave, in that I'm not going to have any code snippets, which is probably a big no-no, but I wanted to kind of touch on a few different questions that are facing the scientific community in how they interact with YT and some of the functionality that you can achieve using a tool like Trident, which I think we're going to see some similar other codes that are shown over the next few days that do similar things in terms of trying to generate observations so we can interact with and make comparisons with observational data. So yeah, oh no. Let's see, is this going to work? Okay. So this is a question, how do we best compare observations to simulations? This is a question that I think really ties a lot of what we're doing to reality. And that is, and I think it's really critical for the kind of the essence of what a lot of us are doing in terms of modeling the universe in some capacity. In this context, I'm talking about astrophysical hydrodynamic data. This could equally be applied to other fields, but this is specifically for astrophysical applications. So a lot of us have numerical simulations of the universe in some capacity, whether it's stars, whether it's galaxies, whether it's cosmology, whatnot. And these come from different simulation codes, and ultimately, at some level, we're trying to compare them with reality. In this case, that's observations from potentially many different instruments. So how do we actually go about doing that? So I think kind of the common language that all of us boil down to, that all these data kind of distill down to, is observational data. And ultimately, I think we as simulators need to distill our numerical data into a form that harkens back to what, like, this universal form, whether it's photometric images, whether it's spectroscopic data or what have you. But ultimately, we need to tie these things to observations because observations anchor our simulations in reality. So as a community, I think we need to produce synthetic observations by using forward modeling of our simulated data sets, as opposed to kind of the reverse. So using realistic physical methods to essentially produce these synthetic observations so that they can be directly applied and compared with true observations taken from actual instruments. And then create open source universal codes for generating these synthetic observations so that regardless of the resources of the research group, everyone can kind of be level-footed and be able to use these tools and compare them one-to-one against each other and against the observational data. So Trident, which leverages YT and borrows heavily from the infrastructure in YT, is an attempt to apply these principles to the circumgalactic medium and the intergalactic medium kind of data set space. So before we get into what Trident can do and so on and so forth, I just want to make sure I know not everyone works in the field of the circumgalactic medium, or let alone in the field of astrophysics. So I just want to talk about what this means for how we observe this data in reality and what it is. So this is kind of the canonical image of the circumgalactic medium. As the name suggests, it's the medium that surrounds a galaxy. In the center here, you have a galaxy, and the disk, the visible parts of that galaxy that are luminous. So something like the disk of the Milky Way or the disk of Andromeda, something like that. But all surrounding that and filling the virial volume and extending beyond that is lower density gas that's being fed by a variety of different sources, whether it's outflows from the interior of the galaxy or inflows from the IGM, but it tends to be very diffuse and low density. And because the emissivity of gas is proportional to the square of the density, when you have this low density gas throughout that halo, it becomes not luminous to where we can really pick it up with the instruments that we have available to us. So much of observations of this are very challenging. So this is a simulation, one of the fire data sets that I've processed using YT. On the left side, you see the density of the gas. On the right side, you see the temperature of the gas. This is evolving from just after the Big Bang to present. And the circle represents the virial radius for this halo. And you can see that there's a lot of stuff that's going on in this halo over its evolution outside of that kind of core central 1% of the simulation of the virial volume throughout. I'll just play that one more time. You see all kinds of gas, the dynamics of which are essentially invisible for a lot of the purposes of what observers are trying to do, because they can't very well see what's going on out there. But it's actually crucial for the understanding of the dynamics of the galaxy and fueling of the stars within it, or quenching of the stars within it, and so on and so forth. So it would be good for us to better model and understand what's happening in there, to better understand how galaxies form and evolve over long time scales. So as I said, that gas is very low density, so we can't easily observe it in a mission, but instead we observe it through observation, of course, through absorption. And this is traditionally done through absorption line spectral studies. So in this case, you've got your galaxy that you care about in the middle, and you've got a background bright quasar, which is the gold thing on the left, and it's producing a spectrum, something like the featureless kind of spectrum that's on the left side. And the observer on the right side happens to have a sight line that connects that background quasar with the observer, and it passes through the intervening galaxy and the halo. And as that light passes through the intervening gas, certain absorption occurs at discrete wavelengths associated with different ions. And that's what these little absorption pits are in your output spectrum. The ions that produce those individual absorption lines tell us something about the state of the gas along that sight line, and in particular in that halo. This is just a phase diagram, since Stephanie was just talking about phase diagrams. The x-axis is the density, the y-axis is the temperature, and you can see that in the lower right corner, the dense cool stuff, you tend to find neutral gas like neutral hydrogen or neutral nitrogen, whereas in the upper left, you tend to find higher ionization lines like oxygen 6 or neon 8. And what that means is when you find those particular ions in your spectra, that reveals some information about the state of the gas, the density of the gas, the temperature of the gas, the metallicity of that gas along that line of sight based on what ions are present. And that's what observers do. These are observational data sets from the COS halos and the Keck baryonic structure survey, showing absorption line features in spectra for various different ions that are listed there. And then the traditional way in which this is used by observers is to categorize how strong those absorption lines are by an equivalent width, essentially how deep those lines are. And then, so that's the y-axis on the plot on the right. And then how close that line of sight is to a kind of a central galaxy, which is the projected distance from that galaxy, or the impact parameter, and you can plot it up as is done on the right side. So that essentially is the right side plot is essentially showing you like how much stuff there is and how far it is away from the galaxies. And by stuff, I mean different ions, but that reveals different things about the galaxy or the state of the matter in the galaxy. So real quick answer, what is the CGM and how do we observe it? The circumgalactic medium is this massive reservoir of low density gas surrounding a galaxy. And we primarily observe it through absorption line spectra. Yeah. Okay, so enter Trident. Trident is a code that was originally part of YT. It broke off and became its own code because it was a little bit more self-contained that way. And obviously it doesn't apply to all of the things within YT. It's specific. What's that? Oh, okay. It's specific to these sorts of studies of astrophysical hydrodynamic simulations. The primary developers were Britton Smith, or R. Britton Smith, Devin Sylvia, and myself, although there have been a number of different collaborators over the last few years, many from the core developers within YT, like Matt or John or Nathan have code that's in there because a lot of this, as I said, was taken out of YT a few years ago. But we've also had numerous contributors who aren't core developers in YT, including Billy Dong, Clayton Strawn, Arina Butsky, Molly Peebles have all incorporated different contributions. So we definitely appreciate all of that. So the two tools that Trident really brings to the fore here, I think, are the ability to post-process simulation data sets and paint on where the ions are. Because most of us aren't doing simulations that include the distribution of all of these different ions, neutral hydrogen or oxygen-6 or carbon-4. And so what Trident does is it can take the fields of density and temperature and metallicity. In this case, I've represented this as a grid, a volumetric data set as a grid, but obviously this applies equally well to particle-based data set and incorporates all of the YT4 support for particle data sets natively. So we take the distribution of temperature, density, and metallicity and feed that into a lookup table that was composed of many different cloudy simulations, and that spits out the various different ions that we might care about. So if you want to see where the neutral hydrogen is, it now is a derived field that sits on top of your data set. If you want to see where the oxygen-6 is, it now is a derived data set or a derived field that sits on the top of your data set. And so that leverages all the other tools that YT has in terms of projection plots or phase plots or what have you. This is that same simulation video that I showed from before for the fire data, but instead of looking at density and temperature now, we're looking at the neutral hydrogen column density and the oxygen-6 column density, which are things that tie back to the observations that we can make direct comparisons with observational data about. And here you can obviously see that these two things look quite different because neutral hydrogen is much more filamentary and tied to the cool gas, whereas oxygen-6 is much more diffuse and associated with the hot gas. So it's much more extended than some of the lower ionization potential lines like neutral hydrogen. But that's just one of the things that you can do. Furthermore, you can run light rays. It's a one-dimensional data object, very similar to the ray or ortho ray object that already exists in YT, but it has kind of applications and ties in some cosmological information as well to what the data set is, what it's probing in the data set. And you can send these light rays as skewers through your simulation volume at any arbitrary trajectory. And then each time you encounter a particular ion that you might care about, deposit an absorption feature in an output spectrum with a Voigt profile and allow those Voigt profiles to be shifted according to the line of sight velocity from the perspective of the observer, much like they would be in reality. Now, this is kind of an on-the-fly demonstration of this. We have a line of sight of one of these light rays that's passing through. In this case, it's a two-dimensional slice of a galaxy simulation data. For simplicity's sake, we're just looking at the line silicon-2 and the ion silicon-2. And so as this passes through that data set, you can see when it encounters matter that contains silicon-2, we see the top panel on the right shows the presence and the density of that material that it's passing through. And then we also see the line of sight velocity in the middle panel on the right, showing if the gas is blue shifted or red shifted to the perspective and the orientation of the observer. And finally, we can see kind of the spectrum, the output spectrum that arises when we deposit these Voigt profiles based on the presence of silicon-2 or not, and whether or not that gas is red shifted or blue shifted, and it produces something like the spectral features that we might expect to see. The green represents kind of the true spectrum, and the black channel map that's overplot on top of it represents kind of a noise added spectrum that something like a telescope might see in less than ideal circumstances. And we can add, in addition, we can add a variety of different kind of steps to make it more observationally accurate with noise, or applying a line spread function that's proportional to, that's similar to what you'd expect with certain instruments like the cosmic origin spectrograph on HST, or other ground-based spectrographs that we might encounter in our studies and want to compare with. So that really allows us to do an apples to apples comparison between our simulation data and actual observational data.
Hey, Cameron.
Yes.
5 minutes.
Got it. Thanks, John. Okay, so application to the circumgalactic medium, as I talked about, you can do these simple sight lines that go through the simulation volume as you have it, but oftentimes we might be trying to calculate the sight lines that are going through a simulation or through a volume that's much larger than the volume that we've simulated. So for instance, if I want to look at the effects of a sight line that goes to redshift of 0.2, well, the distance between redshift 0 and redshift of 0.2 is like half a gigaparsec. And most of our simulation volumes aren't half a gigaparsec in size because that's an enormous volume. So you can kind of analogously do this by layering and processing your smaller data set and looking at consecutive outputs and sending your sightline through the redshift 0.21, spanning that distance, and then stepping forward to the redshift of 0.1 data set, and then continuing that sightline through that, and thus kind of getting around this difficulty. This is a kind of a demonstration of that. Here I have a very simple data set that we're going to send a sightline through from, redshift of 0.1 all the way down to 0. And we're going to go through that data set many, many times, probing the consecutive outputs to produce a spectrum that you can see on the bottom as it's being generated, that's showing the generation of the Lyman alpha forest, as well as the generation of the Lyman beta forest on the left side. And so obviously this is a very simple data set, but as we probe those individual filaments, we're getting absorption, and it's being continuously redshifted to show us this effect. Okay, so Trident is a reasonably mature code now. There's full documentation on Read the Docs. We have a detailed method paper. It supports the YT4 particle data advances that have occurred over the last few years. And in addition, there have been a couple of utilities that have been created to kind of sit on top of Salsa, or on top of Trident. One is Salsa, that was generated by a PhD student at Stony Brook named Brendan Boyd this year. That is really a nice tool for using Trident to effectively generate large catalogs of absorber information from many different spectra. So it's really a practical application of it, and I encourage you to check it out. Similarly, there's a code called CosmoViz, which hasn't yet been fully released by Joe Burchett at New Mexico and collaborators. And I'm going to show really quick, if I may, this in action. Hopefully you guys can see this. So this is a live rendering taking place in a web browser of one of the Eagle data sets. And there are a variety of other data sets that this can be used with, but you can, like Matt was talking about, this is a way that you can interact with a data set on the fly as a user and really explore that data set. And one of the cool things about this is that I can click the Observe button, and then let's say I'll send it through this. Click there and interactively send a sight line, which I can tweak in terms of the size of that sight line. And once I'm happy with the sight line, which I've interactively generated for a data set, actually, this is not that great of a sight line because I went through a void. Sorry, guys. It's not going to be that interesting. I can click request a spectrum, and what it's doing on the back end is using Trident to generate a spectrum along that line of sight that I just interactively identified. Maybe I found a filament that I wanted to go through, so I click I generate the spectrum that I care about. And this is all happening on an Amazon Web Services instance. And then I can click plot, and it shows this spectrum that I just generated. And maybe I'll focus in on like neutral hydrogen at 1216 angstroms. So the bottom plot shows that that's the one that I just generated, and the top one is one that I sent through earlier that went right through the halo region, like the core halo region, where there's a lot of cool gas. And so you can see the presence of neutral hydrogen and some other lines that I don't know what they are. Maybe they're blue shifted neutral hydrogen. I'm not quite sure, but it's a cool tool that allows us to look at a variety of different things in a new sort of manner, and uses Trident on top of it. So, all right, that's all I've got.
Okay, thank you, Cameron.
Yeah.
Can we get some questions? We have a few minutes for questions.
Yeah, let me see.
And use the raise hand feature. Sultan.
Yes, hello, that's very nice. I just want to ask a quick question. Different cosmological simulations like Gizmo and Gadget 3, they store the metals array differently in order. So does Trident take care of that automatically, or? Yes,
actually YT does for the most part. YT is able to recognize for virtually all the major codes. And I know Gadget can be a little messy because oftentimes one can have a different version of Gadget which puts things in different locations. But the bulk of the Gadget code that's being and Gizmo and some of these other codes that are being generated now use HDF5 currently, which self-identifies where the various metal line or the metal fields are, and YT is generally pretty good at recognizing where those metals are, and then that propagates over to the Trident side of things so that we can thus generate these various different ions. At its base level, even if you just have a general metal field, Trident will be able to populate your various ions according to the kind of bulk metal field, assuming some sort of solar abundance, which obviously isn't ideal, but it's a starting point. But if you have a more advanced code that's following individual metals like carbon or oxygen or nitrogen, Trident will grab the appropriate metal field when composing the various ions associated with that element.
So there is no way to manually tell the order of the metals array in the simulation?
You can. There are ways. There are ways when you read in the data set to YT to specify the location of the various different metal fields that might be present. But by default, it does a reasonably good job of figuring that out.
Because I worked in the past, like with some simulations, they have like 9 metals, and some of them they track 11. So
yeah,
sometimes
so
the order is different. So that's why, yeah.
Gizmo and the Fire data sets by default have 11 that it tracks. But yeah, I know it does vary to some extent. And there are ways within YT of specifying that. I can try and find, I mean, not at this moment, but after I'm done here, I can try and find the relevant place in the documentation where you can specify that.
Thanks.
Okay, thank you, Sultan. Any other questions for Cameron? Greg.
Yeah, thanks, Cameron. That was great. I'm a big fan of Trident.
Thanks.
One question you already answered is, are you looking at ways to be able to do sight lines, choose your sight line? And it sounds like, what was it called? Cosmos?
It's called CosmoViz. The primary scientists behind that, Joe Burchett, who was a postdoc at Santa Cruz, who just started or is just starting in the next month at University of New Mexico as a junior faculty member. And he really did this in collaboration with a computer science professor at UC Santa Cruz. And that's where all the volume rendering that we were seeing that's occurring on the browser side has been developed was by this professor named Angus. I forget Angus's last name. Forbes, yes.
Yeah, and they're actually talking tomorrow.
Oh, they are.
Yeah, we had like some last minute excitement, and so
great.
they're talking tomorrow about it. So it's going to be great.
Well, then that was a good teaser for them.
Yeah, it's perfect.
Cool stuff. But what was your question, Greg?
My other question was about, I mean, one of the things that would be, you always wonder is what gas is actually giving rise to what absorption feature. And you showed some nice visualizations, which sort of got to that. But I don't know if is anyone, it would be, are you thinking at all about ways to do that? Like to try, for example, maybe with like lines or something to connect strong absorbers to the gas that they're coming from or something like that?
Right. So
this is, I guess, an extension to YT, but to Trident.
No, but I think it certainly is relevant. I know that there's been some very good work that's been done by the Foggy group to try and do this. So in their first paper, they have a really nice demonstration of it's really an amazing plot showing a sight line that's passing through a simulation volume, and then the various different pieces of gas that it's touching on, and what each of those kind of kernels of gas is responsible for in terms of producing which absorption features and how much they contribute to the absorption features. But I don't think it's a done deal. I don't think it's fully worked out, and that there's a really nice tool for being able to apply this generically. And I think, I think we need to come up with something. I agree with you, and I don't have anything in my back pocket that I can pull out and show you at this moment, but I'd like to talk more about it in the future and try and figure out a solution to this, because I think that's a key aspect.
Well, it's already a great tool, so thanks.
We have time for maybe one more question for Cameron. I will ask one very quickly. Cameron, what are the wave bands? Like, what's the range of wavelengths or photon energies that Trident can be applied to? So I think a lot of what you're showing is UV, right? But can you?
Yeah, I guess I didn't make
go into
that
visible
clear.
Or X-ray or?
And I absolutely should have made that clear, especially given that you're going to give a related talk at some point. I forget when you're speaking actually, John, but so Trident isn't necessarily constrained by a specific wavelength range, although it was primarily developed with infrared, optical, and UV absorption lines. But I know that one user recently has been developing it or modifying it to work with radio 21 centimeter data to generate 21 centimeter observations of the presence of neutral hydrogen. So that's super cool. I don't think that this would work as well in the X-ray realm. So don't worry, you don't have any competition for PyXM. But just because of the nature of the observations of the two, this Trident kind of assumes that we're in a realm where we're not photon limited in the same way that things are in the X-ray realm. So really, it was developed with, rest frame UV absorption line features in mind, maybe even as far as soft X-ray in terms of like neon 8 or magnesium 10, but not into the really hard X-ray regime. And then as far as extending it out in longer wavelengths, certainly the infrared, and now to some extent 21 centimeter and radio observations, but it's definitely line based. Discrete.
Yeah, well, you're definitely not competition, because PyXM only does like optically thin stuff. So you're kind of the opposite. And where it actually may work very well for soft X-ray. So it's something I want to look at, because the future potential missions like Arcus and Lynx, will have spectrographs on them. So
absolutely.
In any case, that's all the time we have, of course. you can definitely continue to interact with Cameron and others in the Slack channel. Right now we have a